Welcome to our session on many-body interactions and classical symmetry-broken magnetism. Today, we are going to focus on how we can understand symmetry-broken magnetism by using mean field theory. And in particular, we will see how we can rationalize this type of emergent states just from a single particle point of view. And afterwards, we will see which states cannot be understood from this single particle point of view, namely mean field theory. And in particular, you will see how just by looking at a Hamiltonian and the single particle interaction that it has and many-body interaction that it has, you will be able to predict what are the electronic instabilities that this Hamiltonian have, and you will rationalize how to trace a many-body grounded state of a system that has symmetry breaking in terms of a fermionic Hamiltonian. The kinds of materials that we are going to focus on are materials where all the interesting physics are given by the kinetics of electrons, by the movement of electrons. And in particular, we can think about two different big classes of Hamiltonians. There are the so-called single particle Hamiltonians, where electrons move almost independently. So these Hamiltonians are effectively written down as a bilinear form. So the way we usually think about these Hamiltonians is that there are annihilation operators and creation operators that we will describe more in detail later on. And what is most important is that there are hopping amplitudes Tij. And the way you can think about these hopping amplitudes is that they give you the probability of an electron being in orbital J to jump to another orbital I. And with these types of Hamiltonians, we can describe a wide variety of materials, and in particular, the electron dynamics of a wide variety of materials. And we can describe insulators, for example, we can describe semiconductors, we can describe metals. In practice, in all these systems, electrons follow quantum mechanical laws, but they follow them in a relatively independent way. So each electron is an individual entity, and it has a movement that does not depend on the other electrons. The most important case and most interesting case is the case of many-body Hamiltonians. In many-body Hamiltonians, we of course have also a term that is like the previous one, so bilinear, but what is most important is that we have a term that is biquadratic in the fermionic operators. So here you have four different field operators, and the important term is that these field operators have an amplitude that is this Vijkl that essentially tell you what is the strength of the different terms that you have in your many-body interaction. And this is the term in the Hamiltonian that effectively governs a wide variety of exotic phenomena in quantum materials. Both classical, symmetry-broken magnetism and quantum magnetism arise due to this term in the Hamiltonian. Charge density wave orders can also be rationalized from this type of Hamiltonians. Superconductivity also arises from this type of Hamiltonians and many other types of strongly correlated states. What is most important is that this way of writing these Hamiltonians with the field operators is a formalism that allows us simultaneously to capture both single particle and many-body physics. And this type of Hamiltonian is what it's called a second quantized Hamiltonian. And the operators C and C dagger are the field operators of the fermion, the second quantization operators of the electrons. So let us start with a relatively simple case. So a case of a single particle Hamiltonian, and in particular, where we have a finite number of sides. So you can think, for example, that we have a chain with L sides, and that atoms that are close to each other have a finite hopping, and the ones that are not close to each other, they don't have any hopping. So the Hamiltonian of this single particle system is essentially C dagger n Cn plus 1, written in a second quantization form. If you look at this Hamiltonian, and in particular, if you look at its eigenvalues, what you actually observe is that when you have two sides, you have two eigenvalues. When you have four sides, you have four eigenvalues. When you have 10 sides, you have 10 eigenvalues. And as you increase the length of the chain, you have more and more eigenvalues, which are, of course, these, let's say, numbers that you would have here in the Schrodinger equation. In practice, if you have a single particle Hamiltonian, the only operation that you need to do in order to find these eigenvalues is to take this Hamiltonian, choose a basis, which is the single particle basis that you define as C dagger n over the vacuum, find the matrix representation of this Hamiltonian, and then diagonalize the Hamiltonian. So if you have L sides, you effectively need to diagonalize an L times L matrix when you represent this Hamiltonian in the single particle basis. And that is the reason why, as you make the system bigger and bigger, you have more and more eigenvalues, and in particular, the number of eigenvalues increases linearly with the system size. A typical way in which we usually look at the eigenvalues of a Hamiltonian, specifically of a single particle Hamiltonian, is by looking at the so-called density of states. So here on the left, you have the eigenvalues of that very same Hamiltonian, and on the right, you have the density of states of that Hamiltonian. The way in which we define the density of states is effectively a delta function of the frequency minus the Hamiltonian. What this actually means is that once your Hamiltonian has an eigenvalue that it's exactly at energy omega, then the delta function gives you a non-zero value, and then in other cases it gives you zero. So what you actually observe is that when you make a heat map of this density of states as a function of the energy, that it's a frequency over here, and the length, you effectively get a reflection of the single particle eigenstates that you have here on the left. From a physical point of view, you can understand that this density of states essentially tells you the probability that you have of inserting an electron in the system at frequency omega. And so, for example, if you do a tunneling spectroscopy experiment or angular solid photoemission spectroscopy, this is the kind of object that you would have access to. So this is the levels in which electrons can live, and that is why the single particle eigenvalues directly reflect what is the spectral function of your electrons. So far, we've just been thinking about single particle models, in particular how the single particle models scale with system size. What is most interesting is what happens when our models go towards the thermodynamic limit, which means that we have an infinite number of sites, and when our single particle models are now interacting. So when we have many body interactions. And in particular, the two cases that we are going to focus on today are the cases where many body interactions in the thermodynamic limit give rise to a symmetry broken state, which is the type of state that we can capture with mean field theory. And we are going to focus on two very specific types of symmetry broken state. We are going to look at classical magnets, which are effectively systems that have a net magnetization due to the existence of finite many-body interactions. And what is important of magnets is that they break time reversal symmetry and spin rotational symmetry. What this means in practice is that even though the Hamiltonian has full rotational symmetry and is time reversal symmetric, the ground state of the Hamiltonian breaks that symmetry. And in particular, if you apply time reversal symmetry to your ground state, you obtain a state that has the opposite magnetization. The other type of correlated state that we are going to discuss is the case of charge density waves. In charge density wave states, we also have a spontaneous broken symmetry, but now this broken symmetry is the translational symmetry of your system. So you can think that originally your Hamiltonian had one atom over here and another atom over there, and the Hamiltonian was completely symmetric. There was no specific distinction between the site over here and the site over there. And when you include interactions, in particular electronic repulsion, what you obtain is that suddenly there's more charge in one side than in the other side. So translational symmetry gets spontaneously broken. The crystal originally had that translational symmetry, but the inclusion of many body interactions give rise to this ground state that spontaneously breaks this symmetry. And so these two cases can be captured with mean field theory. And what is crucial to understand is that mean field theory is a very good technique if associated to the many body interaction, there's a broken symmetry. And this is, of course, the case of both magnets and charge density waves. Let us now look at the fundamentals of second quantization that are going to be important to understand what can we do with mean field theory when it works and when it breaks down. If we think about electrons, we can effectively define two different types of of operators for all electrons. We define the operator Ci, which is the annihilation operator. It effectively destroys an electron in site I. And then we have the other operator that is the Hermitian conjugate, that it's C dagger, that is what we call the creation operator, that effectively creates a particle inside I. Apart from these two operators, we also have a state, that is what we call the vacuum state. This is a state that has no electrons whatsoever, and so when we try to destroy an electron over this grounded state, we get zero. And in practice, you can think that this state omega is a vector, and these operators are matrices. So these operators essentially map one vector to another vector. And when we write our Hamiltonian, we write our Hamiltonian in terms of the creation and annihilation operators. So you can think that the Hamiltonian in this representation is just a matrix. The annihilation operator is one matrix, the creation operator is another matrix, and the Hamiltonian is therefore a matrix. And if you think about two sides, for example, you can want to describe a Hamiltonian that has hopping from site number 0 to site number 1, you would effectively just write this. So what your Hamiltonian does is it takes out a particle from site number 1, and it puts that particle on site number 0, and it does the Hermitian conjugate. So destroying also a particle in site number 0 and putting a particle in site number 1. And so this is the reason why we can think that movement of electrons is just a combination of creation and annihilation operators, because the movement just implies that an electron stops being in one side and starts being on another side. With these operators, we can now start thinking about states that have more than one electron, and in particular that have either no electrons or that they have several electrons. So following the idea of the previous slide, we can now start with our empty state, that is the state omega. This is the state that has no electrons whatsoever, and this is what we called the vacuum state. If we consider that there are in total two different sites in our Hamiltonian, we would just express that this state is the state where there's no particle in site number 0 and there's no particle in site number 1. The other state that we have in our Hamiltonian is a state where there's one electron, and this electron is in the lowest energy state. That it's what we call state number 0. Then we have the complementary state, so the state where an electron is in site number 1. And then we also have a state where both sites are filled. So there's one electron in site number 0, and there's another electron in site number 1. And since electrons are fermions, we cannot have more than one electron per site, and therefore these are all the possible states for two sites in the one-to-many-body basis. A very important question is, how do we impose mathematically this notion that there can be only up to one electron in every single site? So the way this is actually implemented is just by enforcing what are called the anti-commutation relations of the field operators, which in practice, what it means is that you impose that algebraically, C dagger I Cj essentially has this type of mathematical relation, and in particular, if you take two fermions that are two annihilation or two creation operators, you get automatically 0. Having imposed this type of mathematical constraint effectively is equivalent to imposing Fermi-Dirac distribution and anti-symmetry of the full many-body wave function. And this is very easy to understand just by considering how it would be a wave function where you have two electrons, one inside 0 and one inside 1, and see that just due to this mathematical relationship, you would pick a minus sign if you change the order of your particles. And of course, if you try to put two particles on the same side, again, thanks to this mathematical relation, you would get automatically 0. So this is a state that it's out of your Hilbert space. So far, we've been thinking just about electrons, and in particular about what are called spinless electrons. For us, we are going to deal with three main different types of quantum many-body interactions, and in particular, three different types of Hamiltonians that have three different types of quantum excitations. So one of the most important ones is the case of spinful fermions. You can think that this is the most realistic scenario where we can effectively say that in each site of our system, we can have at most 2 electrons. So of course we can have the fully empty state where there's no electron whatsoever. We can have 1 electron with spin down. We can have 1 electron with spin up, or we can have both 1 electron with spin up and 1 electron with spin down, which is the fully filled case. You can think that the hydrogen atom, for example, falls into this class. The case that we originally introduced in the slides is the case of spinless fermions, which is the case where we have one site, and in each site, we can only have one fermion at most. So we have the empty state, which is the state where there are no fermions whatsoever, and we have the state when there's one fermion, and that's all. This is the whole Hilbert space. And then there's another case that will be very important for us, which is the case of spins. And in particular, if you think about the case of spin 1/2, then for spin 1/2, you have 2 different states. You have the state down, and then you have the state up. What is very important is that the spin sites are actually bosonic operators. So the field operators in different sites, they commute instead of anti-commuting, as in the case of fermions. And something also very interesting to note is that you could think that having spins is actually not so different from having spinful fermions if you, let's say, throw this state and this state away. And this is actually the case. As we will see later, if you take spinful fermions and you add a term in the Hamiltonian that quenches how large is the component that you have in this state and in this state, then you effectively get a local spin. From a mathematical point of view, you can think that spinful fermions are just 2 spinless fermions. So you could consider that there's one level for spin up and one level for spin down. And this is a mathematically exact mapping. And then a last important point is that if you have many body interactions, it may actually happen that you have decoupled Hamiltonians for the spin sector of your electrons and for the charge sector of your electrons. And this is what it's called spin charge separation, and it will appear in some of the next sessions. Okay, let us now start looking at some quantum many-body Hamiltonians that in particular have the 2 different types of symmetry broken states that we are going to discuss. So in general, our interacting many-body Hamiltonians are going to be described by this type of Hamiltonian. So we have our bilinear term that again is the single particle term that we can exactly solve. This would just imply diagonalizing a matrix that is linear in the number of sites. And then we have the term that brings all the interesting phenomena, but also it brings all the complications in quantum many-body physics. That is the interaction term. That is a term that has 4 fermionic operators, in particular 2 annihilation operators and 2 creation operators. This term can, of course, have many, many different forms. And today we are going to focus on 2 main mathematical forms. The first one corresponds to having spinful fermions. And this is one of the most important types of many-body interaction, which is the so-called Hubbard interaction. So you consider effectively a lattice that can be a chain, or it can be a square lattice or a zero-dimensional lattice. And effectively, you state that the local interaction is the one that dominates your many-body interactions. And by local interaction, what it means is that you have interaction between spin down and spin up in the same site. So electrons feel each other when they are on the same site, and they do not feel each other when they are in different sites. This is the term that would appear naturally due to electrostatics in your many-body system. So the classical Coulomb electrostatic interaction gives rise to automatically this type of term. And this is, of course, what gives rise to magnetism. So all different types of magnets, including ferromagnets, antiferromagnets, spiral magnets, quantum spin liquids, they can be understood from this relatively simple type of Hamiltonian. The other case that we are going to consider is the case of charge density waves. And so for charge density waves, you can, in principle, drop the spin degree of freedom. You can think that you are working with spinless electrons, and the minimal interaction term that you would have in that case is a density interaction between two nearby sites. So you no longer have interaction between the same site, because if you don't have spin, that is not possible, but you have interactions between one site and the one that is nearby. And you can think that this is effectively what would happen also due to electrostatic interactions. So electrostatic interactions are long-range interactions, and electrons that are in different sites or in different atoms, they still have a finite contribution to the interaction, and this is effectively what you are considering here. So this type of interaction is an interaction that has a tendency to create charge density waves. So you start with a system that has a square lattice, and due to this type of many-body interaction, all your electrons go to this side and no electron to this side, and then this one gets fully filled, and so forth. We have to solve a quantum many-body Hamiltonian, a Hamiltonian that has this kinetic energy and that has these many-body interactions. From our point of view, we are going to consider that the many-body interactions are given. We can take either local interactions or we can have nearest neighbor interactions, but it's important to note that in reality, in actual materials, this type of term in the Hamiltonian can appear due to many different reasons. It can, of course, appear due to electrostatics. So if you have Coulomb interaction, you automatically get a repulsive term in the Hamiltonian. But then you can have contributions to your many-body interactions that come due to the interaction of your system with some other quasi-particle. So if you have, for example, a material that has magnetic order, the interactions mediated by the fluctuations of the magnetic order can actually give rise to another term in this Hamiltonian. Lattices, of course, are made of atoms, and just the vibration of the atoms effectively give rise to other terms in the Hamiltonian. And of course, if you have any other types of many-body interactions, such as plasmons or skyrmions, you can have another contribution to this interaction. They are effective contributions. They are contributions that appear in an effective Hamiltonian, but they are physical and they give rise to correlated states. What is important is that this full combination of different electrostatic interactions and quasi-particle mediated interactions can give rise to an effective attractive interaction or to effective repulsive interactions. In our case, we are going to focus on effective repulsive interactions, which is the case that is most important for magnetism. But it's worth noting that in the very same way that you study this Hamiltonian with repulsive interactions, it is also possible to study it with attractive interactions. Let us go then to the case of magnetism. And for this, we are going to start with the minimal Hamiltonian that gives rise to a magnetic state. This is the Hubbard model. And this is the model where we have local interactions. So we have our free Hamiltonian that is a Hamiltonian in any lattice. It can be a linear chain, it can be a square lattice, and effectively we have hopping between site I and j, the same for spin up as for spin downs. This is a time reversal symmetric term in the Hamiltonian. And then we have our local interaction. So we have interaction between electron down and electron up on the same side. And you can actually think that this type of term in the Hamiltonian can be written as a density-density interaction, in particular, density up times density down. This isn't a greatly challenging Hamiltonian to solve. If we only had this term in the Hamiltonian, it would be very easy. Once we have this interaction term, it becomes very, very hard. And in particular, once you have this term in the Hamiltonian, the problem becomes exponentially hard. So if you have L sides, you effectively need to solve the problem with 2 to the L entries. So an important question that we are going to address is how can we find not an exact way of solving this Hamiltonian, but an approximate one. And by approximate, what we actually mean is the following. If our Hamiltonian was a single particle Hamiltonian, it would be very easy to solve. And we can ask ourselves, is there some single particle Hamiltonian that in a way describes the same physics as the many-body Hamiltonian? And to be more concrete, is there a single particle Hamiltonian whose ground state is the same as this many-body Hamiltonian, or at least close enough? The art of mean field theory is to find what is the single particle Hamiltonian, the mean field Hamiltonian, that actually give rise to a ground state that is as close as possible to the many-body ground state of the interacting Hamiltonian. So in practice, what we are going to do is we are going to look for the Hamiltonian that has a single particle term, the same as the original Hamiltonian, but then that has another additional single particle term that is effectively interaction induced. And finding these parameters of the mean field Hamiltonian is the whole problem of mean field theory. In practice, we can do this in a relatively easy way. So, and the way in which we do it is just by approximating the 4 fermion operators by 2 fermion operators. So you can think that the original Hubbard term in the Hamiltonian was this one. So you had creation, annihilation, creation, annihilation, and then you could take expectation values in 2 of the fermionic operators. And if you start doing these expectation values in all possible combinations, then you would effectively end up with a Hamiltonian that is just bilinear in the fermionic operator. So if you, for example, redefine that U times this expectation value, that it's a number, is M, then you could actually say that the Hubbard term in your Hamiltonian gives rise to a on-site energy in your single particle state that is spin dependent. So the sigma C Pauli matrix is a diagonal matrix that has 1 and -1. So you can think that you are having a positive on-site energy for spin up and a negative on-site energy for spin down. And in this way, you would describe that the magnetic order of your material is effectively just the difference in the expectation values between spin up and spin down. If these 2 expectation values are the same, then you say that your material is not magnetic. And if they are different, then you say that it is magnetic, meaning that it has a finite magnetization in each side. This expectation value is just the total number of up electrons minus the total number of down electrons. So in practice, the magnetization is just the difference in the occupation between the up channel and the down channel. What it's important to note is that this type of approximation, it is exact if U is equal to 0. So if you are in the non-interacting limit, you recover the true Hamiltonian. Of course, in the interacting limit, you don't know if the Hamiltonian that you are recovering is close enough to what you would need to do mean field theory, but in many cases, you will see that it is actually close enough. You can actually do this trick in a more generic way. So if you expect that your system is going to develop non-collinear magnetization, you can start taking all the different expectation values between C dagger up and C down, for example. So if you take this expectation value, you would get the magnetization in the C direction. This expectation value that has up and down gives you next direction, and this expectation value up and down gives you in the Y direction. So mean field theory is capable of capturing, in principle, any type of symmetry broken magnet. You can get ferromagnets, you can get antiferromagnets, you can get spin spirals, you can get skyrmion magnets, all because you actually have all these terms in the mean field Hamiltonian. Let us now think about a slightly different way of understanding mean field theory. You can actually think that mean field theory is a variational method. And by variational method, we mean the following. So let us imagine that you define a very specific state that we are going to call the ground state as a product of creation operators in state omega. This is by definition a single particle many-body state. So you have electrons that are independent from each other. So you are creating one electron in orbital A, another in orbital A2, A3, and so forth. And of course, these different orbitals can be linear combinations of your original sites. And that is what you would have, for example, if you don't have many-body interactions. When you build a many-body state in this way, you are already restricting yourself to single particle states, or to states that are so-called product states or Slater determinants. And now what you can do is the following. You can take this ground state or this many-body state that by definition is a single particle state, and you can try to see how can you find the single particle state that minimizes the expectation value of the energy of your many-body Hamiltonian. So you take that your expectation value of the energy is an object that you want to optimize, and you optimize this object with respect to the orbitals that you have or with respect to the expectation values of your different operators, which effectively is the same. Mean field theory is effectively this type of variational method. You try to look for the product state that minimizes the expectation value of the energy. And the way in which you actually look for this minimal state, for this state that minimizes the energy, is by solving a self-consistent problem. So your mean field Hamiltonian depends on the expectation values, as we saw in the previous slide, and your expectation values determine the mean field Hamiltonian, and the new mean field Hamiltonian gives rise to new expectation values, and so forth. So you iterate this type of cycle many, many times, and eventually you reach a self-consistent solution, and this is the self-consistent solution that in practice fulfills these two conditions. Okay, let us then do this for a very simple case, which is a case of a one-dimensional chain where we have a finite number of electrons. So we are going to consider that we have our nearest neighbor hopping, so hopping between the sites that are closest to each other. We have our local many-body interactions, and then we have a chemical potential. Chemical potential effectively allows you to control how many electrons you have in your system. So if you take one specific choice of your chemical potential, you can get a feeling of your system of 0.2, meaning that you would have 20% of the maximal number of electrons that you could have. You solve this whole Hamiltonian using mean field theory, namely solving the self-consistent problem, and the resulting band structure that you obtain, which is the band structure of the mean field Hamiltonian, looks like this. So you have one band for spin down and another band for spin up. So you can think that this is just a cosine band of the spin down for a linear chain, and this is the another cosine for spin up. And your Fermi energy falls over here. So you effectively have all these single particle states filled and all these single particle states empty and all of this also empty. So in practice, if you count how many electrons down and how many electrons up you have in your system, you have only electrons down, for example. So this is in practice a magnetic system. Electronic interactions give rise to this splitting between up and down, which is called exchange splitting. Again, in the single particle effective mean field Hamiltonian, and your variational many-body state is a state that only has electrons down filled. You can do the same, but in a slightly different case. You can take a one-dimensional chain again, and now force it to be half-filled. A way of forcing a one-dimensional chain to be half-filled without having to put a chemical potential is just by writing the many-body interaction in this form. So in this form, you actually minimize your energy when you have a system that it's half-filled. And you can actually see that this whole term can be rewritten as the conventional Hubbard term times plus a chemical potential. Let us now take, let's say, 2 sites per unit cell. And the reason why we take 2 sites per unit cell is because we are looking for this type of self-consistent solution, a solution where in one side we have spin up and on the other side we have spin down. If you consider first the non-interacting case, which is the case where U is equal to 0, what you obtain is just this type of band structure. So this is just the cosine band that has been folded over itself because now you have 2 sites per unit cell. And what is most important is that it is metallic. When you introduce many-body interactions, you get a gap. And this gap grows as you make U bigger, meaning that as your system becomes more and more interacting, your single particle excitations require a higher and higher energy in order to create. And this is, of course, something that you can look at systematically just by plotting how the eigenvalues of your interacting system evolve as a function of the Hubbard U. So if you don't have any many-body interaction, then your system effectively behaves as a metal. It is gapless. And then as you increase the value of the many-body interaction U, then you see that a gap opens up. And eventually at very large U, the gap is linear with U, and it is approximately U, let's say. So if you look at the difference between this band over here and this band over there, you effectively get the value of U. And this is, of course, something that it is much easier to see if you look at the spectral function of your electrons, that in practice, it reflects the same information as the eigenvalues, but it's, of course, more physical. So if you are in the case with U is equal to 0, you effectively have a system that it's metallic and that it has a continuous density of states. And then as you increase your interaction, so you go to 4U, then you see that a gap starts opening up, and eventually the gap becomes linear with U. So you can think that this is the type of object that you would measure if you do spectroscopy in your material. When doing mean field theory, there's something that it's incredibly important. We are solving a self-consistent problem, which is a nonlinear problem. In order to solve it, you need to give an initial guess. In order to do this iterative procedure, you need to start with some guess solution. The guess solution that you use as a starting point, in a way, determines what is the end solution that you're going to get. So you could start, for example, with a guess that it's fully ferromagnetic. And if you do the whole self-consistent loop with a ferromagnetic solution, you're going to end up in a ferromagnetic state or in a non-magnetic state. And if you make as initial guess the anti-ferromagnetic solution, then you would end up with an anti-ferromagnetic state or a non-magnetic state. So you can actually think that for the same Hamiltonian, you actually have two solutions. And of course, each Hamiltonian needs to have one ground state or a set of ground states that are energetically equivalent. And these two states are very inequivalent. So this state is metallic and ferromagnetic, and this one is anti-ferromagnetic and insulating. So a very important question is which one of these ground states is the actual real one? Which state actually has the lowest variational energy? And this is something that one can compute systematically. So you can actually take, for example, a one-dimensional chain, solve it at the mean field level, and use both a ferromagnetic guess and an anti-ferromagnetic guess. And when you reach the converged solution, you can actually ask yourself which one of those two solutions has the lowest energy. And you can plot the energy as a function of the interaction U. And if you do that, so if you look at the energy difference between up and down, what you actually observe is that the energy difference between these two states is always positive for very large U, and then it slowly goes towards 0. And if you look at the specific sign, what you actually see is that the anti-ferromagnetic solution is the one that has the lowest energy for a chain at half filling and only first neighbor hopping. And if you look at the scaling of this energy as a function of U, you will see that it has a 1 over U dependence, meaning that if U is infinite, the two solutions are equivalent, but when U is finite, they are inequivalent. And this is something that will appear again later on. Let us go to the strongly localized limit. So the limit where U is much, much bigger than the hopping, and most importantly, the limit where we can actually map our problem of spinful fermions to a problem of localized spins. For this, let us start again with the one-dimensional interacting chain. So we have our kinetic energy and we have our local Coulomb interaction, which is called the Hubbard interaction. And for large interaction strengths, we have a local magnetic moment. The first important thing to note is that if U is very, very large, you see that the local magnetic moment per site approaches 1, which is the maximal moment that you could have in each site. If you're at an intermediate value of U, you don't have a finite spin in each site, but when you are very deep in the interacting limit, you have a finite magnetic moment, and in particular quantized magnetic moment on each site. So this is the limit where we are going to be interested in the following. And to understand this, let us start with the simplest Hubbard model, which is a Hubbard model for just two sites. So we are going to consider that we have hopping between these two sites, and then we have our local interaction in each one of the sites. And we are going to call these two sites 0 and 1. And for concreteness, we are going to focus only on states that give rise to a half filling in the whole system. So we are going to consider that we have two electrons, and we are going to count only the states in the many-body basis that have in total two electrons. So the states in the many-body basis that fulfill that condition are different. So we can have up and up, down and up, two electrons in the second site, two electrons in the first site, or the previous states reversed. And this is everything. These are all the elements of the basis of the many-body Hilbert space if we are at half filling with two sides. In the strongly localized limit, there are two emergent families of states. So there are the states where we have just one electron per site, and these states have energy approximately 0, or the energy given by the hopping. And then there are states that have two electrons per site. And when U is very, very strong, these states are very, very high in energy. They are at an energy distance on the order of U. So if you think that U is 100 times bigger than the hopping, then you would have 4 low energy states that correspond to single particles, to single occupancy states, and then a high energy state that has two electrons on the same site. So in practice, if we try to write down a low energy model for our system, then that low energy model is going to be a low energy model that gives rise to this type of Hilbert space. So we can have up in the first and up in the second, down in the first, up in the second, down in the first, down in the second, up in the first, down in the second. This is the Hilbert space, but of course, the Hamiltonian can still see some dynamics of the high energy states, but our degrees of freedom in the Hamiltonian will be these ones. So in practice, just by looking at these states, one can realize that we have effectively spin 1/2 at each site. So we started with a model that had electrons with spins, and after including many-body interactions, we end up in the low energy sector only with spins. An important question is, how do we find the Hamiltonian that describes the dynamics in this low energy sector? To do this, we are going to use second order perturbation theory. And from a mathematical point of view, one can already anticipate that the low energy Hamiltonian must have this form. And the reason why it needs to have this form is because the Hamiltonian does not break rotational symmetry. And therefore, the only Hamiltonian that you can write down with spin operators is S dot S if you want to have the lowest order in product operators. You can, of course, also write down a biquadratic form. And then there's going to be a parameter in front of this that is J. And this is the parameter that we effectively need to determine from second order perturbation theory. When we do second order perturbation theory, we just need to identify two different terms in the Hamiltonian. We need to identify what is the pristine Hamiltonian, the bare Hamiltonian. This is the Hamiltonian in which we know the eigenstates. And then we have to identify the perturbation in the Hamiltonian. This is a small term in the Hamiltonian that is going to modify the states a little bit, and it's the term that is effectively going to give rise to the dynamics. If we are in the strongly correlated limit, in the limit where U is much, much bigger than T, then We take that our pristine Hamiltonian is the Hubbard term, meaning that this is the term for which we know the eigenstates, which are the states that we discussed in the previous slide. And then the mixing term in the Hamiltonian is going to be the hopping. And in particular, this is the term that it's going to mix the low energy manifold with the high energy manifold, meaning this is the term that is going to mix the states that have just one electron per site with the states that have two electrons in one site and no electron on the other side. And these two different sets of states is what we call the ground state manifold and the virtual state. So when you apply second order perturbation theory, you effectively just need to compute matrix elements between the ground state manifold and the virtual state. And those matrix elements are just the hopping, right? Because the hopping is the term V that connects a state that has down and up with a state where the two electrons are just in one atom. So you can think that the hopping just moved this red arrow from the left to the right. And if you apply the formula from second order perturbation theory, you see that you effectively get T squared over U. So T is the matrix element between ground state, virtual state. U is the energy difference between the two manifolds. So in practice, you can actually use this very same trick not only if you have two sites, but if you have an arbitrary number of sites. And in particular, if you have sites forming a one-dimensional system or a two-dimensional system or three-dimensional system or anything else. So in general, if you have a Hamiltonian that has hopping between site I and J, and then it has local interaction Q, you can use the trick from the previous slide in order to systematically map this model to a spin model. So you take the limit where U is much, much bigger than T. In that limit, you have only one electron per site at most. And then you apply second order perturbation theory to every single pair of sites. And for every single pair of sites, you are going to have a term that is Tij absolute value to the second power over U. And this is going to define what is the exchange coupling that you have in your effective spin model. So in particular, the strongly interacting limit, a Hubbard model at half filling maps to a Heisenberg model for spin 1/2. In general, you can actually think that this type of mapping from electrons to spins is not unique to having just one electron per site, but if you have a multi-orbital problem that has several electrons per site, such as in d orbitals, then you could map to a more generic Heisenberg model. And that is actually the case. So if you have, for example, two electrons per atom, you can map that strongly interacting problem to a Heisenberg model with spin 1. If you have three electrons per site, you can map it to spin 3/2, and so forth. And if you have systems where apart from the orbitals of your interacting electron, you have other orbitals of weakly interacting electrons, then those orbitals of the weakly interacting electrons can give rise to new contributions in your Heisenberg model. The mathematical form is always like this, but these extra orbitals can actually change what is the sign of your exchange coupling. And in general, you can have antiferromagnetic coupling, which is in a way the easiest case to obtain, but in others you can actually have ferromagnetic coupling. And in the presence of these terms in the Hamiltonian that break the original rotational symmetry, and in particular terms that couple the spin degree of freedom to the spatial degree of freedom, then you can have anisotropic couplings. So couplings where the x, y, and z directions are not equivalent, but where your Hamiltonian actually breaks the symmetry. And this is what happens quite often if you have strong spin orbit coupling. Okay, so if you have a Heisenberg model, one always needs to remember that the spins that you have in the Heisenberg model are quantum spins. So in principle, they have commutation relations. But very often it is also convenient to think about them as if they were classical objects. And if they are classical objects, you can think that a spin is just an arrow in space. It's just an angular momenta. And if you just solve the Heisenberg model classically, you effectively get two different ground states. So you get this ground state if your couplings are antiferromagnetic. So this is an antiferromagnetic order. The ground state breaks time reversal symmetry, and you have up electron on one side, down electron on the other side. And then if you have a coupling that is ferromagnetic, then the low energy state is a state where you have up in the two sides. And it's important to note that these are classical ground states. These are ground states that assume that your spins are classical, which in a way, it's a very similar approximation to mean field theory for magnets. So if you use that approximation to solve, for example, a square lattice model or a honeycomb lattice model, you can actually obtain that in the square lattice model. At half filling, you get this antiferromagnetic state. In the honeycomb lattice model, you get another antiferromagnetic state. And in practice, these antiferromagnetic states are equivalent in a sense that both the square lattice and honeycomb lattices are bipartite, meaning that you can separate the sides into sets, A set and B set. A set is always up, B set is always down. And you can identify those two sets just by looking at these plots. What is most interesting is when you consider magnetic order in frustrated lattices. So in lattices that are no longer bipartite, and that is the case of, for example, Kagome lattices or triangular lattices. So in a Kagome lattice, you effectively have a set of triangles and hexagons, but if you try to find two different sublattices, you will not be able to find them. And if you solve the Heisenberg model at half filling, what you obtain is a ground state that has a spin spiral magnetization. So the magnetization points in one direction in this side, in another direction in this side, and another direction in this side. It rotates by 120 degrees between these three sides. And then if you go to the replicas in another unit cell, you get exactly the same magnetization. So you can think that this is a periodic magnetic arrangement, but it's a magnetic arrangement that is different from ferromagnetic and antiferromagnetic ones. And in the triangular lattice, you obtain a very similar phenomenology. So the magnetization rotates by 120 degrees between this side and this side, and the system is periodic, let's say from this side to this side. These are classical states, and this hold if you solve the Heisenberg model with mean field theory, or if you solved the associated Heisenberg model, assuming that the spins are just classical quantities, that they are just a vector field. When one goes to the many-body limit, the ground states for these systems are completely different. Okay, so now the last term that it's interesting to discuss is the case of non-isotropic exchange couplings. And these are the couplings that break the rotational symmetry of the Hamiltonian. They are still bilinear in the spin operators, but they do not have SO3 symmetry. So they do not commute with the generators of rotations. And what this means in practice is that they make different directions of the spin energetically inequivalent. And there are many different terms that can appear following these conditions. There are maybe three very important ones, which are the following. One is antisymmetric exchange, which is a type of term that appears if you have broken mirror symmetry. So if you have a system where what you have above and what you have below is different, and this effectively promotes at the classical level non-collinear order. So you can think that the energy of this system is minimized once this arrow and this one form 90 degrees. Another important term is the anisotropic exchange, which is effectively a term that drives the system towards a classical solution. So if you have a system that it's only described by this type of term in the Hamiltonian, then you would have a so-called Ising model. This is a model where only the C direction of the spin is coupled. And this model is purely classical. This type of term in the Hamiltonian appears if you have, for example, strong spin orbit coupling and single ion anisotropy. So your spins stop being quantum and become more classical. And it promotes magnetic orders where the spins want to all lie in the plane, or they all want to lie along a very specific axis. And then another term that is very important is the Kitaev interaction, which it is like an anisotropic exchange that it's bond dependent. So between this site and this site, Z are coupled. Between this site and this site, XX are coupled. And between this site and this site, YY are coupled. So this term, by construction, promotes magnetic frustration because, of course, there cannot be a ground state where the spin points up X and Y at the same time. And this is a very important term in the realm of quantum magnetism. So far, we have been focusing on Hubbard model, but it's important to note that a very similar set of phenomenology appears if we consider an interacting model for spinless fermions. So if instead of thinking about spinful fermions, we now think that we have spinless fermions with the minimal electronic interaction that we can write down, then we would have our conventional hopping for spinless fermions and a density interaction between one site and the next site. This type of interaction promotes charge density wave orders. And in particular, you can think that this Hamiltonian has two very different sets of ground states. There's the ground state for V equal to 0, where your system is effectively non-interacting, and you have just a linear chain with hopping, where the occupation of every single site is 1/2. So this is a metal, and you can think that's a featureless metal. You are not breaking any symmetry in this system. Now, if you go to the limit where V is much, much bigger than T, then the ground state that you obtain is actually a state where this site is completely filled, so the occupation number is 1. This site is completely empty, so the occupation number is 0, then 1, then 0, then 1, then 0. So the original translational symmetry of the chain got broken between many body interactions, and you end up with a state where charge accumulates in one side and it's completely depleted on the other side. This is the charge density wave state, and it appears for repulsive interactions in this model. And this is something that one can very easily show just by solving this many-body Hamiltonian using mean field theory. So the technique is very similar. One essentially decouples this interacting term into terms that are bilinear in the fermionic operators, and the other two operators, they get transformed into their expectation values. And when you do that, you effectively obtain the following. So if you plot the spectra as a function of the interaction V, what you observe is that the system remains gapless for V equal to 0. And then as you switch on V, the system gets a gap that becomes bigger and bigger with V. And if you look at the energy difference between the occupied band and the empty band, you observe that the energy difference is on the order of V, and it, of course, keeps growing linearly. And this type of phenomenology is, of course, much easier observed if you look at observable, like the density of states. And when you do that, you see that in the density of states, in the absence of interactions, you have a metal. And then as you switch on the interactions, then you get a gap opening in your spectral function and a nearly linear growth of the occupied states and empty states with the interaction. From a phenomenological point of view, the spectral evolution of your electrons is very similar between this model and the Hubbard model. But it is important to note that in terms of symmetry, the ground states are completely different. This ground state breaks translational symmetry, whereas the Hubbard model at the mean field level breaks time reversal symmetry. And in particular, this is something that can be systematically computed. So you can look at the charge imbalance between the two sides in your chain when you have this nearest neighbor interaction, which in practice you define as the occupation of one side minus the occupation of the other side. And if you have a large system, you can define it as the occupation on each side, and it alternates between even sides and odd sides. If you have 0 interaction, then the imbalance, the charge imbalance between odd sides and even sides is 0. And then as you increase the interaction, then the imbalance becomes bigger and bigger and bigger until eventually at very large interactions, you have that even sides are fully filled and the odd sides are fully empty. So far, we have been focusing on cases where mean field theory holds, or we have been assuming that mean field theory holds. Mean field theory is a fantastic tool to understand the impact of many-body interactions in quantum many-body models and to get intuition about what is the ground state that one may get once many-body interactions impact a very specific single particle model. However, mean field theory breaks down sometimes. And as we will see in the next lectures, we are going to focus mainly on those cases where mean field theory breaks down and we have to rationalize the physics of the model using a full quantum many-body model that accounts for all the quantum many-body physics that cannot be captured by mean field theory. What we are going to do now is we are going to look at a minimal model where we can directly see that mean field theory breaks down. And for this, let us take a Hubbard model. So in general, in a Hubbard model, we had, let's say, our hopping and our interaction. And when we look at this model, what we observe is that the model does not break time reversal symmetry. So you can apply any spin rotation or time reversal symmetry to this Hamiltonian, and the Hamiltonian remains the same. If you look at the mean field Hamiltonian, for example, a mean field Hamiltonian where you assume that the first side is up and the second one is down, then the mean field Hamiltonian itself breaks the symmetry. And when you break the symmetry in the mean field Hamiltonian, then the ground state that you obtain is also going to break the symmetry. So one has kind of a complex situation here where the exact Hamiltonian does not break symmetry, the approximate Hamiltonian breaks symmetry, and therefore the approximate ground state breaks symmetry. And if the true ground state does not break symmetry, then a limitation of mean field has arisen. So let us now look at a concrete case and see how one could actually overcome. Okay, so let's start with the Hubbard timer. So if you look at the Hubbard timer and you start plotting or start computing the solution as a function of increasing and increasing many-body interactions, what you obtain is the following. So the solution of this many-body Hamiltonian can be done with mean field theory, and you can look at the gap in the single particle spectra of the mean field Hamiltonian, and you obtain this type of evolution. So first, the gap remains constant, and eventually it grows linearly. And this type of change in the gap is actually associated with a change of the symmetry of the mean field Hamiltonian. So up to here, the mean field Hamiltonian is time reversal symmetric, and suddenly from this point onwards, the mean field Hamiltonian breaks symmetry, in particular time reversal and rotational symmetry. So this case over here is the case where you would have almost quantized magnetization in each side. If you look at the exact solution of the Hubbard timer, you actually do not see such breaking of time reversal symmetry. So in particular, if you take the Hubbard timer and you go to the strongly localized limit, where you can map the Hubbard timer to the Heisenberg model, you could just try to write down the exact solution of this Heisenberg model. So the exact solution of a model that has spin 1 and spin 2, and that they are quantum spins. They have commutation relations. If you just look at the many-body spectra of this Hamiltonian, what you actually observe is that the true ground state of this Hamiltonian is the singlet. So it's a linear combination between down-up minus up-down. If you solve this Hamiltonian at the mean field level, in the strongly interacting limit, what you obtain is that your ground state is either a state where you have electron up in the first side and electron down on the second side, or the opposite, or something in the X or Y direction. But what is important is that mean field theory will never give you a state that looks like this. And the reason why it will not is because this state is not a product state, even in the fermionic representation. This Hamiltonian is one of the minimal Hamiltonians where the ground state cannot be written as a product state. And this is the type of many-body Hamiltonian for which a much more powerful method has to be used in order to capture its specific physics. And this is what we are going to address using exact normalization and tensor networks in the next sessions.